Hey, what's going on, folks? It's Mike here, and welcome to the next lesson in our Modern C++ series. In this lesson, we're going to be taking a look at something important in C++ when it comes to working with iterators. Now, I've been looking at iterators in the standard template library, and have even created some of our own. But regardless, this is a problem that we need to know about, which is known as iterator invalidation. That is to say that our iterators sometimes might not be valid or actually accessing our data structure as we're traversing through that data structure. Now, this isn't a problem that just applies in C++. Even if you're using something like Python, you need to think about this. So let's go ahead and define the term. We'll look at some drawings and try to understand what this problem is and exactly when we can use iterators and when they get invalidated. This will also inform us a little bit as we've been looking at these previous lessons of how to create our own iterators, and you could probably even think of some smart ways to create safe iterators that would know if they're in an invalid state. So anyways, with that said, let's go ahead and look at CPP reference and try to understand this problem here. So I'm going to go ahead down to the containers library here first. And if you scroll down a little bit, you will find this nice table talking about iterator invalidation and what happens when an iterator becomes invalid. But before we revisit this table and take a look at some code, let's go ahead and just draw this problem out first. So what I'm going to go ahead and do is draw out some contiguous data structure, maybe something like a vector. So let's just go ahead and draw it here, nice and big here. And let's say we have a few elements that I have pushed in here. And it might even be worthwhile to add them in here. Let's put 10, 20, 30, 40, and so on. And this is our vector data structure. We're going to assume that the capacity is 4 elements, so it's fully allocated. And then we want to start working with this data structure. So let's go ahead and write out some code, for instance, that we might write, where I grab an iterator, and I'll actually write out auto iterator equals this vector dot begin, and I'll write auto maybe end equals vec dot end, and then I'll have a for loop here. I say for, I don't have anything. Here's my sort of start condition, and I want to say, well, the iterator is not equal to the end. Then we do plus plus on our iterator and proceed to do some code. So far, this is fine. And maybe even we will just print out these elements in this code block here. But what happens if I decide that I want to do a vec dot push back here? Now, this would be some interesting code, but you could imagine some sort of branch condition in here, and we'll actually look at this when this happens. But let's just say I want to keep pushing back 5 here. So we're effectively extending this data structure here. But let's go ahead and draw all the pieces here, because I do have this iterator here that's pointing to the beginning. So let's go ahead and indicate that here. I do have this end that's pointing to the end here. So if I'm doing a pushback operation and extending this data structure here, is the end still valid? Well, not within the context of this for loop, because that's always going to be pointing here. And even worse, what we said is that the capacity of this data structure, if we assumed it's 4, it might reallocate to make room for this new element that we're adding in here, this 50 or this 5 or whatever we add in here. So now let's go ahead and pretend that we did this pushback here. Let's do pushback of 50. And the data structure has to reallocate. So that means somewhere else in memory, so I'm just going to draw here next to me, I'll have 10, 20, 30, 40, 50, and maybe some extra space for some other elements here. But where are my iterators pointing? They're pointing to some other memory that might have gotten unallocated. So this is the problem, and we would say our iterators are invalid. So I'm just going to go ahead and scratch them out. So this can happen anytime, again, we change the shape of our data structure. So in the case of a vector, we're changing the shape by extending it. And a list, we might be changing how it's arranged, or a tree data structure. This all applies the same way. So modifying our data structure, let's just go ahead and write this rule down here. Modifying our data structure invalidates our iterators. Okay, so this means things like remove operations, pushback operations, push front, or I'm just going to put in parentheses here, insert, any sort of insert type of operation here, okay? Now it's fine for us to just read from a data structure. That's not going to invalidate it, right? Because there's no chance that the data structure is going to grow and maybe have a heap allocation or shrink due to removing items. And these types of operations can be hidden in many different places here. So let's actually look here at our vector data structure. I'll go ahead and open this up here. I do want to keep our iterator table here, but let's just play a little game here where if we look at some of these operations, we can think about what will change our data structure. And again, just looking at this table here, this is true for all of our STL data structures, we can kind of think about based off the category that they're in if they're going to invalidate any current iterators. So if I'm just accessing something, maybe changing the element, that's probably fine, okay? In most cases here. In fact, in all these cases, it should be fine here. Here is actually getting our iterators, so that doesn't have anything to do with it. But here are capacity operations. Let's think about some of these. Do any of these look suspicious? And I'll give you a chance to pause the video. You can hit spacebar or pause and see if any of these look suspicious. Now, if you did that little exercise where you paused, what about this one? Shrink to fit here. Well, that would be something that changes the shape of my data structure here. See, our vector, let's go ahead and just bring it over here. If I was going to take this here and say, well, I don't actually need this extra element here, but with my iterators, if I shrink this, that might allocate this in a new block of memory, something that's exactly 5. Okay, so I might get an allocation over here that has 10, 20, 30, 40, and 50 in it. And thus this gets freed from memory, but our iterators still point, in other locations, depending on how many iterators we have. So even shrink to fit, again, would be something that changes the size of our data structure, thus changing its shape here. Okay, so that's the idea here. So again, these can be hidden if we're not careful. Although anything that is inserting or removing, I should say, changes our data structure, so it shouldn't be that much of a mystery. So under modifiers, this should be a clear hint that these are things that could change our data structure. And again, things like push back might not seem like it, or push front, but again, we might get a heap allocation behind the scenes that changes our data structure. So that's the idea here, okay? All right, so let's go ahead and look at this in code because I think we understand the idea and just see some of the effects of changing our iterators. And it might also be worth now looking at this table, actually, so we can kind of see or anticipate what's going to happen. But our vector here, after insertion, let's go ahead and see, are our iterators valid? Are references, or after erasing, are they valid? And we do have yes in the screen table, but that says before the modified elements, okay? And that's only if the capacity didn't change. And I kind of gave you the more extreme examples where you do a pushback and that reallocates the data structure in a bigger block of memory elsewhere. So in most cases, we should just consider our iterators invalid in this case if we're doing something of that nature, okay? Otherwise, you can see here on our table here, reading vector, our after insertion, modified, well, at or after the modified elements, they could be okay, okay? All right, so let's go ahead and take a look at this in action here. So let's just go ahead and create some vector here, and we'll use the example we have, 10, 20, 30, 40, 50, 60. Let's give ourselves enough numbers here to work with. I included type info here just because I always like to show some of these modern uses because we haven't seen them every once in a while, where we can get the type ID of vec and print out the name, just because I want to check that these are in fact maybe integers or longs. Let's go ahead and see and compile this. And let's see. Well, we can't really tell here. It looks like it's probably integer here, but let's be sure. After we're just working with ints. And again, I like some of these things like the class template argument deduction. Looks like it did assume it is a integer. The type signature didn't change, but it's probably better to be explicit. So anyways, have a few of these little things here. And why I include this, because again, if you're working with your iterators, you might want to see what you're getting back and so on, because I'm going to be using auto. Just a little reminder there. But anyways, let's go ahead and use some sort of loop here and modify our data structure. So let's just go ahead and say that we do an iterator here, auto it equals our vec begin. And while we're not at the end of our data structure, we'll move that iterator forward. There we are. And let's just go ahead and start off by printing things out here, slow and steady here. Dereference the iterator, which retrieves the element, compiles, and it runs just fine here. So print out the type, 10, 20, etc., etc. Okay. So again, something that we might do here or think about doing, or is common to try, at least when we're starting out here, is to say, well, I'm already looping through this data structure. I'm printing stuff out. But what I want to actually do is say if this element here is equal to 30, then I want to remove it from my data structure. Okay. So we need to think about how we can remove things from our vector a little bit here. So let's think about how we do that here. And we'll have to go into the vector here, look at our modifiers, and it looks like we do have a way to erase here. Now, eventually we will be looking at these standard algorithms, so make sure you subscribe so you don't miss that. But let's just go ahead and look at erase here, specifically for vector. And let's go ahead and see here how we do this. So it looks like erase, let's actually read from here. It needs some iterator for it, okay? Whether it's a constant iterator, or we can also remove a range of elements by providing 2 iterators, okay? 2 positions, again, for our iterators. Okay, so let's go ahead and look at the code here. It looks like we could just erase the beginning element if we wanted, or we could move by, whatever index we're at. This is erasing a range, so between the 2nd and the 5th elements from the beginning, and so on. But let's go ahead and see how we do it here. I mean, we have an iterator here. So it must be that if our iterator is at pointing to the element that is 30, then we can just erase it. So let's go ahead and do vec.erase, and we have our iterator here. So let's go ahead and try that. Let's see what happens. Compiles just fine here. And I run it. And I get 10, 20, 40, 50, and 60 here. Okay, so this is kind of interesting here that this actually works here, or it appears to be working for what we have. But let's go ahead and see from CPP reference if this is a valid operation to do something like this here. Okay, so let's go to CPP reference. So this is a sequence container. That's where vector is. And we're in erasure here. So is our iterator invalid? Yes or no? So as long as we are, let's see, before the modified elements, okay, as long as the capacity didn't change here, okay? Or I could say at or after modified elements. Okay, so it looks like I was deleting the element that we had here. Okay, very interesting here. And let's go ahead and play around with this a little bit here. Okay, so let's go ahead and say that for now this isn't crashing. But what if we want to do some sort of other operation here? Like, let's go ahead and try something else, like a pushback in here as well. So let's go ahead and basically say, well, if we find an element here, whatever it happens to be, 30, then we want to sort of push it back and almost rotate it to the end, right? So you can sort of imagine this as just taking every element, maybe at the front of a collection, and just sort of pushing it back in a queue. So let's go ahead and see what happens there. Let's go ahead and compile this. I'll run it. And, well, looks like we still get 30 here. So this seems to be working just fine. And in this case, it probably is fine because, well, we're retrieving a new iterator at the end after we do the pushback operation. So we are probably okay. But let's go ahead and play around with this code a little bit here. Let's go ahead and say I grab the end iterator here. Auto, I'm just going to call it end here, which is going to equal our vec.end. And let's go ahead and say if I'm not at the end here. Okay, so this would be more close to what a range-based for loop's doing. Go ahead and recompile this, rerun it, and it looks like we're still okay for this data structure. But let's go ahead and try to see if I do this twice here. Okay. So again, let's go ahead and get rid of element 40, push it back, and go ahead and rerun this and try again. And it looks like, again, our rotation is working. And it looks like we just haven't changed the size enough here. So let me play around with this a little bit here. Let's get rid of that pushback here. Rerun this. Okay, now we've got a problem here. So it looked like this was working here. And this is the tricky thing with the iterator invalidation and why we just have to be careful when we change things. I knew if I'd play around with this, I knew it was already broken. But the issue here is, well, I've got 10, 20, 50, 60, 30, and then I get a segmentation fault. Because, well, I'm removing elements. We think the end is still available, meaning that we can just keep pushing back, but we're modifying the vector data structure. So where the end is, or again, remember that the end iterator is this special memory or in the container here. Let me go ahead and draw it on one of these examples here, right? So in this particular example, right, this might be the end block here, but if I'm getting rid of, say, 30 and 40, right, and rotating 30 towards the end here, we basically never hit a valid end location here, okay, in our actual heap here. Let's look at a few more examples here and see how we can fix this. Now, in order to actually do a little bit better with this, though, what we can do is try to update this iterator here from erase here. We should actually look closely at this erase function and see that it does return an iterator here, okay? Now, if we actually read through this description here, and most of these functions you can read, it says invalidates iterators and references at or after the point of erase here, okay? So one thing that you'll see folks do in code is, right, when we can make sure that this iterator is okay, IT, but again, let's go ahead and read this carefully. It says invalidates iterators and references at or after the point of their erase, okay? What iterator is after? Well, this end iterator here that I've created here, okay? So again, then we are kind of done here. So where might this be okay to have this sort of for loop with some iterators and then we want to erase stuff? Usually what I say is, don't do our modifications here. What we want to do is probably just break out of this loop immediately, okay? So that would be a paradigm where it's fine. You don't have to worry about invalidating the iterators. You can just effectively treat this algorithm as maybe finding and erasing an element here. Okay, if it exists, then erase it, right? It's some sort of linear search, okay? Then it doesn't matter if we've invalidated, these other iterators here. And in fact, I would encapsulate this code to have it just like we did. Okay, so this is like a linear search and remove elements safely, okay? And that would be fine here, okay? But otherwise, we don't want to leave our elements here. Oh, let's see, what did I get? Vec.end, the parentheses. Let's make sure I compile it. We don't want to leave our iterators otherwise in a bad state. Okay, that's the idea. So here we can see how I ran it here. I was able to find element 30, but previously, that was after 10 and 20 here. So that's no problem. So I hope this sort of makes sense, this idea of iterator invalidation, and it's worth looking at this table here to just see the different ways that you can invalidate an iterator. My general rule is that any time that you have iterators pointing to some data structure and I modify it, meaning I erase or insert an element, I'm just going to treat all those iterators as potentially invalid. That's the safest approach to look at this. Now, I'm sort of leaving this a little bit on a cliffhanger because I do want us to think about, perhaps in the next lesson, if that'd be interesting to folks, is how could we define a safer container that works with iterators such that we could maybe invalidate those iterators themselves, or think about, just a safer structure for this. Now, of course, if you're being very careful, as shown here, and maybe we have a bunch of iterators pointing to this data structure, and we do an erase, for instance, it's fine, right? Those iterators pointing to the previous elements. Although, as I mentioned here, the last thing I'll mention about this is if I do vec, shrink to fit, after doing a bunch of erases, that could allocate a new block of memory somewhere else. In fact, let me actually look at shrink to fit here. See if that's true, if it'll actually heap allocate somewhere else. Let's see if our iterators get invalidated here. Invalidation. Oh, we've got a nice list here. Well, it looks like this will still cause problems. If vector change capacity, all of the iterators will be invalidated, which again makes sense. So we have to be careful with all these operations overall. All right, folks, so I'll go ahead and leave it there. As always, if you didn't catch those other iterator lessons where we build one from scratch, look at some of the other standard template library ones, feel free to check out my website here where you can track your progress and make sure that you're watching those lessons. Sometimes the order matters and it's useful to watch those previous lessons, so check those out if you haven't already, but you can track your progress on the website if that's more convenient. Otherwise, folks, thanks for your time and attention. Thanks to all my members, supporting, and subscribers and viewers, and I'll look forward to seeing you in the next video, and maybe we'll talk a little bit more about iterators or safe iterators. Let me know in the description, in the comments below, excuse me, and we'll go ahead and take a look at that perhaps in another video.